Right, we're all present and correct. So welcome along. So yes, this CPD is really an introduction into to fan coils. Anything you've got to ask, let's go through them at the end. We can do a bit of Q&A. Both myself and Ashley are technical people, both engineers, but we work in sales. So yes, we should be able to answer most things. Anything we can't, we can obviously come back to you. So obviously the purpose of the course is just to give you that basic insight into fan coil technology and also understand benefits over some of the other technologies. Obviously, we also cover some basic technical calculations and things to be aware of when it comes to how we select the fan coils, and it helps sometimes with the design side of things if you consider the necessity of some of the information that we need. So the content that we'll run through is a little bit about air conditioning and fan coil units, a little bit on the F-gas regulation, chilled water versus VRF, a bit on air conditioning, then the calculation and sizing, a little bit on the basics of acoustics. We do a CPD on acoustics itself, which is a little bit more in depth, specific fan power, and then just a brief run through of a couple of case studies that we've done. So air conditioning fan coils, very sort of basic. So the air conditioning side of things is basically the control of temperature and humidity in a defined space. Then the applications of that are either comfort or close control. Most things that we tend to deal with, although there are close control applications we are working with units that have humidification and dehumidification in, is comfort cooling, and that is essentially the ability to keep a space at a particular temperature. So the fan coil itself is a simple device. It consists of a heating or a cooling heat exchanger, or coil as we tend to call it, and a fan, and that's why it's called the fan coil. It is essentially a heat exchanger and a fan within a box of some description that houses those two components, and that can come in various different sort of forms, which we'll see as we sort of progress through. But essentially, it's used to control the temperature in the space, or to control the temperature in multiple spaces. Nowadays, controls-wise, it can be as simple as an on-off switch, a thermostat. It can be controlled through a BMS or a BEMS for the management system, which is then controlling the water through the heat exchanger to control the valve and also the fan speed to adjust the actual performance. And units can be either exposed or concealed, ducted or non-ducted. So sort of different variations that are thereabouts is up in the top left-hand corner is a typical ducted unit. It can have round spigots coming off the front, which will attach to ductwork and then to outlet grills. In this particular instance, it's a rectangular grill, which could be used for more of a sort of hotel bedroom, a bulkhead type installation, where it'll go through a rectangular discharge plenum onto a grill. It can also house the valves, as this one depicts here, which for space constraints have been sort of taken back outside the rear of the unit. Then we've got cassettes next on the sort of top right. Variety of different sizes of cassettes on the market, from a typical 600 by 600 fits in a normal ceiling tile, up to something that's more sort of 900 square, which is obviously a larger capacity. Bottom left-hand corner, we've got can be concealed, but could be on show is a cased wall-mounted unit. These can also be horizontal type units that will sit against the ceiling. Like I said, they can be cased or uncased. We'll have a look at those in a bit. And then a traditional wall-mounted unit, which is a high-capacity wall-mounted unit, and it sits high up on the wall. So typically, and apologies, there's quite a lot goes on in this slide. It sort of shows a bit of all of the units in different positions, but the idea of it is just to show where that you would normally mount and how these would normally work. So if you took that typical fan coil unit, generally it's probably installed above a ceiling where we've got a return grill. We've got some fresh air coming into the back of the unit, and then that would be ducted out into the space through the ductwork in the plenum. It could have a return air plenum on, which we tend to see more in more hospital medical type applications where void air that could be contaminated doesn't need to be used, and they want to return from the actual room straight through the fan coil and back into the room. Let's move this box out of the way. Then we've got cassettes. So cassettes typically sit in a false ceiling. Again, they can be free hanging, 2 different sizes, but they work by drawing the air in through the center of the unit, through a filter, and then the fan spits it out, and essentially through that heat exchanger. And normally you have that sort of what we call a 4-way blow cassette, which can either have adjustable outlet vanes, which will either push the air down if it's in heating, or across the ceiling if it's in cooling, which makes use of what they call the Coanda effect, which we'll mention shortly. Then we've got a wall-mounted unit, which would be sat typically high wall. So this particular wall-mount unit draws the air in through the sort of bottom and through the bottom front, and discharges that out of the top. And the reason that does it on this particular unit is to make use of that Coanda effect. So the Coanda effect is simply if you push that cooled air across a surface, it helps to cling to the surface. So by making use of the Coanda effect, either from a cassette or a wall mount that has a top discharge, it allows it to cling the surface of the ceiling for longer. So it allows it to serve a bigger room, and you get a bigger throw into that room. Typically what you'd find on a wall-mounted unit is typical, like a DX split type unit, where you would have it actually on a rotating vane at the bottom. Those sorts of units won't make use of the Coanda effect. So this is specifically designed for that benefit. And then we have the wall-mounted units. So as it depicts here, you could either have a cased unit, these could be colour-coded to an environment, or it could be a chassis unit. So again, you can find these in hotel receptions, in schools, bedrooms, that sort of thing. Certainly hotel bedrooms, where it could either be mounted behind an architectural cabinet, so you put a chassis unit in, depending on what the surroundings are, or you could mount it in a colour-coded case or a plain white case, which is the standard.
On the wall-mounted unit, how close to the ceiling does it have to be mounted to get?
Ideally, you don't want to be too far away. We normally say within 50 mil of the top of the ceiling, so just enough to be able to get the case off to service it. But the higher up you go, the better you get the cling across the ceiling. Yeah. Bottom right-hand unit, you've got something that's a bit more of an industrial unit. This is a close control unit. You're not going to fit these in your typical bedrooms and office spaces. There have been gyms, server rooms, IT rooms, material storage, areas where you need to control the temperature, but you also need to control humidity. So if it's delicate paperwork or artifacts, or it could be something as simple as computer IT equipment, that sort of thing. That's where you find this sort of unit. Generally is a higher capacity, anywhere up to, this particular unit will go up to 20 kilowatts, but it is a little bit more of an industrial type unit. So for the main components of a fan coil, we've got the fan motor. Nowadays, everything is EC-DC. We don't, and most manufacturers will not really make AC motors anymore. Some of that is down to legislation and the ELP directive, but most of it is meeting building efficiency levels that are required. You've got the coil or heat exchanger. These are usually divided into 2 different types. We either call it a 2-pipe fan coil, which means you've got a flow into the unit and a flow out, or a 4-pipe, which is a flow in for the cooling, a flow out, a flow in for heating, and a flow out. On the 2-pipe, it could be a cooling only unit, it could be a heating only unit, or more days we call them a changeover unit. So if you're using it with something like a heat pump, some more of the renewable technology, then you would find using it for cooling during the summer. And then as it gets to the winter months, you just switch the heat pump over, reverse cycle it, and put that heating water through that heat exchanger. The benefits of doing that is, especially when you're using a lower temperature hot water by making use of that larger coil, which you would normally be using for cooling, allows you to get reasonable capacities out of it to serve the sort of performances that are required. So there are lots of benefits for doing it. With valves and actuators, obviously that does depend on specs, but nowadays most specifications are calling for PIC valves, although 2 and 4 port valves do still exist, and we'll run through valves a little bit more shortly. And then, as we mentioned, we've got controls. So it depends on the application. Most applications now are going to have controllers on, which are going to be linked to a BMS network. But depending, it could be as simple as an on-off. It could be just a simple thermostat and a time clock. And most of these can be accommodated by the manufacturers. So the F-gas, I'm not going to go through sort of war and peace on this. I don't know how much people sort of know, but it does sort of link to the growing market within chilled water technology. So people may have heard of ozone depletion or ODS gases, and these were the things that were like R22. They created the hole in the ozone layer. They're now banned and gone. And the new thing is GWP, which is global warming. And I think most people have heard of global warming when they listen to the news and read things. So GWP, it stands for global warming potential, and it essentially is the term that's used to measure the environmental effect of a substance in relation to CO2. So most people see CO2 and think, well, it's really bad. When it comes to refrigerant, CO2 is the best refrigerant you can get. So from a GWP perspective, if you had 1 kilogram of CO2 and it leaked out into the atmosphere, that would be equivalent to 1 kilogram of CO2 up into the atmosphere. If you're looking at traditional refrigerants that are used in VRF systems, so 410A is a good example, that has a GWP of 2088. So if 1 kilogram leaks out of a VRF system, that's equivalent to 2088 kilograms of carbon. And that is quite a lot. So it's typically about the amount of carbon released by a normal commercial jet that would be flying between the UK and Florida, let's say, somewhere over in the States. So it is quite a lot. And that's why the F-gas regulations exist. They are there to try and get under control the GWP of the refrigerants out on the market. So 404A, worst offender, that's now pretty much banned. That was very much used for refrigeration in supermarkets. So all of the freezers and cabinets that you see in a supermarket, they were traditionally working on 404A. And as you can see, that carries a GWP of nearly 4,000. So it's a pretty nasty environmental chemical. Most supermarkets are obviously moving over to other technologies, stuff like CO2 and also A2L type refrigerants. But this is where the F-gas regulations come. So a little bit of a snapshot on it. Back in 2015, when the F-gas came in, it came in with basically 2009 and 2000 to 2012 average amount of refrigerant that was placed on the European market. So it started at this 100%. And then over the years, 2018 being the first, what was known as the F-gas cliff, suddenly lost 37% of the refrigerants on the market. We're now obviously in 2024. So as you can see, we're 69% down from where we started in 2015 in terms of the actual availability of some of the high GWP refrigerants. There are lots of things that you read in the news and read in the trade magazines regarding refrigerant and the trading of refrigerant. But essentially, the idea of this regulation is to phase out all the nasty high GWP refrigerants and replace them with more environmentally friendly ones. So CO2 is an environmentally friendly one. A2L refrigerants, which are mildly flammable, are quite low. You've also got some of the more natural refrigerants, like R290, 1270, which are flammable refrigerants, but have now quite widely been used in heat pumps and other systems. So this is the real change, is to get that average GWP down from an average of 2000 by 2030 will be down at 400. There has been some legislation, or is imminently going to be released since the UK's exit from Europe, where Europe have released their targets, and the UK will be slowly coming behind, but will at least be meeting EU, if not trying to better them. Yeah, so some sectors, as it says there, will find it more difficult to change because there will some of the actual requirements, whether it's performance, there are certain drivers that and constraints on the new refrigerants that stop them moving over. One of which, when we talk about VRF, as we mentioned here, is flammability. So flammability is a concern. So some of the legislation at the minute will stop you putting some of the mildly flammable refrigerants into a system in volume. So a typical VRF system might have hundreds of kilograms. You will not be allowed to do that, and you can't do that as part of the legislation using something that's mildly flammable for reasons of obviously creating explosions. So there is the flammability concern of it. There is the misuse of it, where you're always going to get people out there trying to put retrofit certain refrigerants in systems that they weren't designed to be. You know, the results of those could be catastrophic. Chill water, it's water, runs around a building, it's not going to set fire, it's future-proofed. Doesn't matter what the chiller's doing out on the roof or down somewhere else, that can have an A2L or an A3 refrigerant in it, because actually the legislation around it, because it's outside and the technology such allow that. So it just makes chilled water an easy retrofit to put in, knowing it's future-proofed, without selling somebody a system that will be redundant in less than 10 years. There are no HFCs in the actual fan coils in the water system. Obviously the chiller itself or the heat pump will have a refrigerant in. It's also a flexible installation, so you can hang a chilled water fan coil, you can move it, you need an electrician and a plumber, you don't need an expensive installation and commissioning engineer to go and reclaim all the refrigerant, vacuum the system back down, and then to actually charge it again. And as it says there, it's exempt against the tightening refrigerant leak controls, which is another big area aside of the F-gas, obviously where leaks occur. To stop leaks, the leak controls coming in are very, very tight. I'm not going to go through this slide in detail. You can have a copy of the presentation afterwards. This is not it's not a one-sided view. It is a view that has been raised by FETA. I'm a member of the FETA committee for Fan Coils, and it is openly out there. It's on the website. It has been viewed by people in other FETA groups. So it is a sort of collective perspective of things. But yes, essentially, it's just giving you things from size to positioning to sound levels, and showing that the fan coil is by no means a bad technology to be using instead of those VRF type installations, where we are as an industry trying to make headway and obviously take market share from that refrigerant market.
Do you look at the cost at all?
The costs are that we have got some cases, so we have got some information, and it does ever change from capital costs and installation and ongoing costs. We have actually got some information, and I think we have actually got some on chill beam as well. So it's chill beam, VRF and fan coils. Again, it's a sort of recap really of the slides we've just said. Chill water tends to be more beneficial when it comes to large installations. So it could be large residential, it could be large commercial, hotels. We talk about the life cycle cost effectiveness there. So yeah, we can send some of that information over. Less maintenance required than a VRF system. It hasn't got to have regularly F-gas checks, year or multiple times a year, depending on the charge of the system. Has a minimal global warming potential, doesn't have to comply with the F-gas regulations. You've obviously got free cooling that can be optimized on the chiller itself, which is not obviously part of the fan coil, but part of the system. Easy, adaptable and flexible to mount them in different positions without the cost of expensive engineers. Still get very good temperature tolerance and control of the space temperature. And obviously future-proofed against the rising cost of refrigerant, which is at times, and it does fluctuate. It has settled a little bit at the minute, but if you go back a couple of years, it was about 800% of what it used to be. So a kilo of 410A used to be about £15. It was up in the hundreds, and the availability was pretty next to none. So there is obviously a future proof against that, and that's only ever going to get tighter as the quota in the EU and across the UK goes down. So in terms of performance, these are the sort of things that we sort of consider on a daily basis when we're working on specifications. It's the thermal performance, total and sensible, the external air temperature, water entering and return temperatures, noise requirements, the external air resistance, hydraulic flow resistance, leaving air temperature and specific fan power. And this is probably the minimum that any fan coil manufacturer would probably require in order to give a sensible and accurate selection of product to meet the requirement. So we'll run through some basics first, of just the basics of what we talk about when we talk about dry bulb, wet bulb, humidity and dew point. So as we mentioned, dry bulb. So dry bulb essentially is, and I'll put it on, oh, skipped on one. So what is it? So dry bulb is essentially what most people see, whether it's on a thermometer in an office, it's in the car, it's at home on a wall. It's the temperature that's physically measured. What the wet bulb is the measurement with a wet gauze where you've got a completely saturated bulb at the bottom of that thermometer. So essentially when we talk about wet bulb, it's also a conversion through into humidity level. So if you had a 100% saturated temperature on that wet bulb where you have 100% humidity in the room, you're not going to evaporate any of the water off that particular gauze that's wrapped around the bottom of that thermometer. So you've got 100% humidity. If you only had 10% humidity in a room, that the temperature and the water on that wet gauze will very quickly evaporate. And that evaporation of water from that gauze around the bottom of that thermometer is essentially, it creates a cooling effect. So if you see a dry bulb and a wet bulb, which are exactly the same temperature, you're essentially 100% saturated. If you have a wet bulb temperature, which will be lower than the dry bulb, depending on the level of where it is, will give you an actual moisture content, which will give you a humidity. Oh, there's something missing up there. When it comes to dew point is the temperature at which you create condensate. So if typically on a fan coil, we work at 23–50%, typical office UK standard conditions, at 23 degrees, 50% of the air is saturated. So the dew point is the point at which the amount of moisture in the air becomes a temperature that is 100% saturated. And that happens to be about 12 degrees. So you've got 50% moisture, it's in the air, everything is fine. It cools down to 12 degrees. That humidity is now 100% saturated in the air, and anything below 12 degrees means it can't hold on to that moisture any longer, and it gives it up as a condensate. So best way we normally describe this is you take a Coke can out of the freezer or the fridge, you stick it on the side, it's nice and warm in your house. Within about 5 minutes, you get condensate running down, and it's the same effect. You've got moist 23-degree air suddenly hitting the temperature side of that can. It rapidly cools it down. Can might be at 3 degrees, so the air that's in contact at that point could be down at 5 or 6 degrees, and at that temperature it can't hold the moisture it had when it was at 23 degrees, so it gives it up as a condensate, and that's why it sweats and runs down.
Excuse me a minute. Have you lot worked on your psychometric charts? Because this all goes back to your psychometric charts, and you should understand that.
Yeah, I mean, we can do some bits on psychometrics if you want to.
If you find a dew point.
Yeah.
If you go across the other way, I'll show you how much water is dropping out.
Yeah. Yeah, it's very good to understand the psychometrics. People get frightened when you pull the psychometric charts out, and it's actually very interesting to start plotting things and then find your way around, because it does tell you a lot and help you a lot. So then we move on to the sort of thermal performance, and we've got total cooling or heat gain, as we call it, and sensible and latent. So most times when we're selecting product, because there's usually an air handling unit that's taking account of most of the moisture in the building, the latent loads, we're normally working on what we call a sensible. And sensible is the pure temperature control of the air. We're not talking about controlling humidity and moisture levels. We're talking about purely about temperature. But total is a combination of the two. So sensible heat is the temperature, and latent heat is essentially the phase change. So if you've got that 50% moisture at 23 degrees, when you use 6 and 12 water, you've got that 23 degrees coming to a mean temperature of about 9 on the water. It's going to create evaporation because you've gone below that 12 dew point. And at that point, there is a certain amount of energy that was required to convert that vapor into that liquid, and that is the latent heat. So the two of them together give you the total cooling. So it's very easy done on a calculation. I think most people, and if they haven't, again, we can run through these sort of things. Total duty, it's an easy calculation. It's the specific heat of water, 4.187, 4.2, whatever you want to use, the mass flow rate of the water, which is easily measured, and the delta T of the water. So from things like witness tests for clients, total duty is the one that's mostly used because most people have got an accurate flow meter, accurate temperature sensors on your in and out of your pipe, and 4.187 if you're not using any glycol in the system, and that will give you a very accurate total duty. In terms of sensible, I need to take that line off, it always stays there. It's a very similar calculation, but because you're working with air, you've also got density of air. So it's the specific heat of air in this case, which is 1.004. The mass flow rate of the air, well, we know what the airflow rate should be. We can measure the airflow either using pitot tubes or using a flow hood. Roughly, we know the density air at a particular temperature, 1.205 is fairly standard. And then we can measure the air going into the unit and the air coming out of the unit. And those all multiplied together would give you a sensible duty. You can also use some of the enthalpy differences to calculate sensible as well, which you can get from your psychometric charts. But that would give you a good way of calculating sensible and total. And it's surprising how many times we work on specifications where people ask for things, but when you actually add them all together, physically it doesn't work, and physics is physics and you can't change it. It's a balanced equation. If you want this duty, you've got that flow rate and you've got these temperatures, there ain't a lot you can do other than get that result. So when people ask for results but try and constrain you to other fixed parameters, it just doesn't work. So yeah, going back to physics is always the best way. Return air temperature. So again, we talk about this 23-50%. That is typical. It's used for most UK selections. However, there are obviously other different temperatures depending on the applications. Typically, an increase to 24 degrees, 50%, gives you approximately 10% more cooling duty out of a unit. So it is a consideration when you look at capital outlay of equipment. Actually, if 24 is a reasonable value to use, then obviously it can save the capital cost to the client. There is the consideration of mixed air temperature. So when people are bringing fresh air in, 18 degrees is very typically a fresh air temperature from an air handling unit. We're mixing it with the 23. That's going to give a mixed air temperature. Could be 21, 20, 22. But that lower temperature onto the back of the unit is going to reduce the performance of that unit. So it's also a consideration when looking at it. In terms of the difference between what we see on spec when we refer to air on or FCU or room temperature, FETA and the HVAC Fan Coil committee publicise on their website that if somebody is talking about a room temperature, then it is absolutely fine to assume between a 1 and a 1.5 degree uplift in that temperature by the time it gets into the back of the fan coil. So if somebody talks about maintaining 23 in a room, we'd probably use 24 or 24.5 into the back of that unit, because above a ceiling void, you've got lights, you've got heat generating, heat risers against a concrete floor there. Therefore, you do pick up that extra temperature, and that is used as a publicised way that manufacturers can work. Obviously, we've talked about being ducted or terminated, just using the return air intake. So you can return duct straight from the room, so that 23 would go into the back, or it can be mixed up into the void space and drawn from there. Chill water temperature. So typically 6 and 12 was always the temperature that was used from a chiller, and then there was this shift to sort of move towards the 10 and 16 and 8 and 14s, which is great. It was more efficient for the chiller. It did mean that the performance of fan coils was slightly reduced because you just can't get the performance at the higher temperatures that you could at the low. I think nowadays 6 and 12 still seems to be the main runner, and that purely is down to chiller manufacturers have obviously got the technology and the compressors and the performance to be able to deliver those more efficiently. As we've said before, dew point 12 degrees C, which is used on 6 and 12. So 6 and 12 will produce some condensate because that mean temperature of 9 coming into contact with air at 23, 50%, it will drop below the dew point and you will get some condensate. The benefits of using the higher temperatures, such as 12, 17, very sort of usual for things like chilled beams, is because it sits thereabouts and around and above the dew point, you won't get any condensate. And in those types of sort of calculations that we would do, you would see your total duty and your sensible duty identical because there is no phase change, there's no condensate produced. Obviously, when it comes to heating, there is never any condensate, the phase change because it's heating, so total equals sensible on heating always. In terms of heating, again, 8271 traditionally used. There is a reason why the 8271 is very much an American thing, is where those temperatures, because they do seem like an obscure set of temperatures rather than 8070. But again, they do fluctuate. Generally, those sort of temperatures are going to come from a boiler plant. You see 6040 could be coming from condensing boilers. 5535 is now commonplace, which is a mixture of condensing boilers or heat pump renewable technologies. And also 4535 is quite common, where we're purely using the heat pumps. And I have seen one the other day, which was absolutely frightful, where they wanted to use 25 and 18, which produced zero output from the unit whatsoever. But they are driving down now. And as manufacturers, the design of the units are more optimized to these technologies now, so you can get reasonable outputs from the higher chilled water, lower heating water. Right, and acoustics. So acoustics, we typically talk about two different things in our industry: sound power, or SWL, or sound pressure, SPL. So my little example on the right-hand side is the sort of best way I've always found to describe it to people. So sound power is an energy, doesn't change. If you have a 2 kilowatt heater in the corner of a room, it gives out 2 kilowatts, whether you stood at the back of the room, in front of it, or in a completely different room, it's always giving 2 kilowatts out. So that's what we say is the sound power. It's an energy, it doesn't change, nothing can change it, not the room size, whether it's outside, inside, it's doing what it does. When it comes to the sound pressure, that's a sort of temperature. So if you go and stand right in front of that fire, you'll burn your legs. If you stand at the back of the room, it'll be a lot cooler. And that's more like the sound pressure. So sound pressure essentially is something that will change with that environment. So if it's got soft furnishings, it's got a carpet, it's got soft seats in, it's got ceiling in, then those things, it's curtains, not too much glazing. They're all things that can alter the characteristics of the sound that is heard in that room. The energy doesn't change. It doesn't change at all, whether it's in that space or in a different space. But the actual what you hear does. Whether you stand in front of the unit, you stand at the back, you will hear a different sound level, but the energy doesn't change. So there's the two ways to sort of think about it. The power never changes, the pressure will do, and it changes with different spaces. And that's quite important when it comes to actually selecting the right bit of equipment to make sure the sound levels in a space are not exceeded. So most specs nowadays will talk about asking for an NR. An NR is a particular curve. It's used in UK and Europe. You may have also heard of NC curves, which typically tend to be American. But the NR relies on assumptions being made by a manufacturer. So if it's a typical office, then we or other manufacturers will have an idea in their head that we're talking about a large space. There might be reflective surfaces, there might be glazing. So you apply some knowledge to that in order to make the best selection, that when that equipment goes in and you want an NR of say 25, that we give you 25 or 35, and it doesn't end up being something different. So as we said, NR is based on the sound pressure, so it does depend on the intended space. If that room is very different from a typical normal environment, then there will be an effect for this. So one of the examples I gave, which is actually a real life situation that we came across, we actually did two different jobs quite close space of time to each other. So it was one particular unit, it was the same unit, and one was actually used in a lab where it's got hard surfaces, wipeable surface, stainless steel, hard floors, or a typical office type environment. And the same unit doing exactly the same duty at the same airflow gave an NR that was as much as 8 to 10 different from each other. So 35 in an office, but in the lab it was 45. So that's the sort of thing you have to bear in mind when we're doing those selections. When we talk about sort of, and it's more installation wise, obviously there are ways in which we can get the NRs down. So typically nowadays we have what we call inlet attenuation. Inlet attenuation allows you to attenuate some of the noise that comes out the back of the unit. Typical inlet attenuators might be used on a ducted fan coil where there is no ceiling. So it's more that architectural look where the sound, which travels in straight lines, comes out the motor straight through the back of the heat exchanger and falls into the room. So there are things like that that can help. The two little diagrams I show here, the first one, which is on the left, is where you have got return grills and they've been poorly placed right behind the fan coil. So essentially the noise comes out the back of the unit and dumps straight through the grill, straight into the room space. Ideally, which is never ideal because there's lots of surfaces up in the ceiling, you would really want to offset a bit like on the right, where behind and to one side. So any noise that comes out, yes, it travels in a straight line. Because the grill is offset, some of that ceiling can attenuate some of that noise, and it does soften and make the actual inlet noise a lot less by the time it actually goes into the roof space or the room. So yeah, one of the issues with NR as well is, and we'll come on to specific fan power, is how it actually affects the specific fan power, and how sometimes if we've got unrealistic NRs, you can then end up having to oversize units to meet the NRs, which is again a higher sort of capital cost. Resistance, so this is more air now. So typically we will work around 30. It's a UK standard. That accounts for ductworks, for bends, for plenums, for grills, and also the tortuous path that sometimes the air has to take from being in the room space to getting back to the rear of the unit. And that is what we call the external air resistance. The unit itself has a resistance. We take that into account because that's a known, but the actual external is unknown to us. But as I said, 30 is the usual. Anything less than that is brilliant because it actually helps with sound, it helps with efficiency, with specific fan power, and we do see more and more specifications now, you know, driving down towards the 20. As I mentioned, on efficiency, sound levels, you do get the benefits. When it comes to hydraulic coil resistance, there is a rule of thumb that 2 kPa per kilowatt of sensible cooling. So 20 kPa if you've got 10 kilowatt cooling output. And we try and stick to those because having too much of a resistance on the unit, it will affect pipe work, it will affect pump sizing, and obviously there is an expense to running lots of big pipes around a building with an oversized pump because fan coils have been incorrectly sized with high resistances. So we try and keep to those rules of thumb. In terms of specific fan power, so specific fan power is effectively the measure of the efficiency of the actual fan in this particular case. So it's measured in watts per litre per second. So it's how many watts it requires to deliver a particular litre per second of air. So as it says there, typical fan coil units use between 1 and 5 fans. So yes, sometimes having more fans in there can mean a lower SFP, doesn't necessarily mean it is higher. It all depends on what the actual level. All fan manufacturers will design their fans with a sweet spot in mind where it is particularly the most efficient, and it isn't usually at the bottom. Right at the bottom end, you tend to find most fan curves are more like a hockey stick, because you need a particular amount of energy just to get the fan moving. So it's a really low airflow. The SFP can actually be quite high, but actually as you ramp that fan up towards its sweet spot, that's where you get the best efficiencies. Again, unrealistic SFPs can mean oversizing of FCUs, which is obviously a higher project cost. I have seen specifications now where people are striving for 0.12 of an SFP, which is unrealistic. And as I take most people back to Part L, which has only been re-released in the last 18 months, 2 years, I don't know where it was now, is it went through various iterations, and the drive originally was to drop to 0.35 on fan coils, and they didn't allow it to happen, and it got put back to 0.4, used to be 0.5. So as I say to most people, yes, efficiency is absolutely paramount. It's absolutely what we want, but 0.12 is unrealistic, and 0.4 in Part L has been put there for a reason, and that's because sometimes you can't get anywhere near 0.12. And most fan manufacturers will testify to the fact their fans can't produce it either. So one of the things I sort of draw on, and I probably need to update this slide, is I was part of the BSI committee with the Feed to Fan Coil group. There's about 6 of us as manufacturers who have actually, and it is launched, it came out in 2020, BS 8850. And the reason for that was to create a level playing field and a standard that says how, as manufacturers, we should measure our specific fan, because it was the one thing that wasn't legislated. So from manufacturer to manufacturer, you can apply your own assumptions to what SFP was. And we could say it's 0.2, one of our competitors would say 0.14, and it's just who's willing to take what risk to say what it will do. But ultimately, under BS 8850, both fan coils will probably perform exactly the same. So that was what 8850 was about. And I'll be honest, it's been a slow push out into getting consultants, people to use BS 8850, because it isn't actually legislated and actually policed by anybody, but it absolutely is a good measure between fan coil manufacturers. It does go on to actually specify how the test results should be given to customers, so that every manufacturer produces their test report in exactly the same format. So it's easy for somebody to say, right, this was this, this was this. It's easy to compare. So that was what BS 8850 was out. But yes, it is out and there. It is out and running. There's case studies. We will briefly sort of go through these. This is obviously things we worked on, but it just gives you an idea, really, the sort of applications where fan coils can go. So this was a Microsoft headquarters over in Ireland. Lots of ducted units in there. It was a mixture of ceiling, architectural, and also fancy drapes and latticed ceilings where the acoustics were absolutely paramount. So there was quite a lot of design work went into the actual acoustics, and there was a specific attenuated design just for that particular project. This was a large residential, heart of Westminster, 800 ducted amber units. So the amber unit of ours is a little bit slimmer. It's about 235. But again, supplied with full controls and PICV, which is sort of commonplace now for manufacturers selling the basket of products. Royal Liverpool Hospital, we always tend to do well in hospitals. When we talked about some of the products, because as a manufacturer, we have ducted, we have wall mounted, we have cassettes, we have close control, we have what we call our topaz units, which are cased, uncased ceiling and wall mounted units. When it comes to hospitals where you've got nurses' stations, you've got back offices, you need a bit of all sorts, and therefore, from a specification, we tend to do pretty well as a one-stop shop for all products. Crossrail, very interesting product for anybody who's of my sort of age and older, who remembers the King's Cross sort of fire. The anything for Transport for London or that has a TfL spec now is very onerous in terms of what sort of equipment can go down into these stations. They can't have anything that's flammable. There can be no plastics. So we ended up having to design a range of units that was completely metal, no plastic products whatsoever, and any cabling was all low smoke, zero halogen cable, just to meet their specification. And that's gone into some of the Crossrail projects, certainly on Paddington. One of my favourite case studies, so this was down in the Midlands, down in Loughborough. This is again Sapphire units, PICV also controls packages, and that's for what was known as DNRC, which is the Defence National Rehabilitation Centre, which was for mentally and physically injured personnel, and is a mixture of living quarters and sort of rehabilitation centre. And then on that, any questions? I'll try and cover a bit of everything in there. So I appreciate it goes quite quick. So if you've got anything, fire away.